Well, I really feel extremely honoured to be asked to talk at this meeting to celebrate Dennis's birthday, especially to be the second oldest speaker. Dennis, the phrase larger than life size seems almost to have been invented to describe Dennis. I met him more than 40 years ago, and almost at once, somehow, he changed all my view of mathematics, and a great deal of the mathematics that I know derives from him. Of course, mathematics that I know derives from many people, but one way in which Dennis stands out is he was able to make me feel that even in areas of mathematics that I had never felt the tiniest interest in, there were fascinating questions to be answered. Dennis is somehow being interested in everything. Many people have mentioned his wonderful seminar and experiences in it. I'm not going to talk about my experience in it, but one of the things that being sort of a data, I felt that Dennis's seminar was just one of those examples. Biologists tell us that structures like the eye evolve independently in different regimes and so on, and I thought, well, it's just the Gelfand seminar somehow evolved independently in New York. But there's something about Dennis's seminar which I don't think I've met in any other place, which is Dennis's ability somehow to be the best listener in the world. When you talk to Dennis, you really get heard, and even people often who have very murky ideas and could very easily be neglected, Dennis will hone in on them and extract the real idea that lies down there, often very incorrectly expressed. Anyway, I'm going to try and talk about quantum field theory. And I've always been interested just simply in defining it. One reason for that was explained very well in the very first talk we heard of the speaking by Smirnov, when he was explaining that there were these problems within his lattice models, which once you saw that the thing was somehow controlled by a two-dimensional conformal field theory, all sorts of miraculous things could suddenly be discovered. The hard work, the difficult thing, was seeing that somehow you were in the neighborhood of that regime. Now, so a quantum field theory is meant to be something which is very kind of rare and somehow very close to being rigid. It's a very mysterious but very kind of crystalline thing. There are not meant to be very many of them. People believe that above 2 dimensions, quantum field theories form at most finite dimensional families, and probably among above dimension 4, there aren't any at all. There's meant to be nowadays a 6-dimensional theory which just sits there completely ununderstood like a 6-leaf clover that no one can say very much about at present, defying all the rules. Well, nevertheless, although a quantum field theory is somehow very rigid and crystalline, it's surprisingly hard to say exactly what it is. And so that's what I've tried to do. So let me begin this talk, at least, by talking about the traditional way quantum field theories are formulated. So the traditional formulation is to say, and I'm going to sort of only consider a very toy model of the situation. So we're going to be talking about a d-dimensional space-time, which I'm always going to think of as being Riemannian rather than having a Lorentzian metric. So in the traditional way of describing theory, then for each point in X, so this is meant to be a d-dimensional field theory, and for each point of X there is meant to be assigned some vector space of local fields or observables or whatever. So not an algebra or anything, but just somehow some mysterious thing that you're somehow meant to be able to observe at the point. And the data is all meant to be contained in the following thing. When you pick a certain number of disjoint points, distinct points, x1 to xk, then there's an expectation map, a multilinear map, often written like this. If you take something all the data is meant to be contained in giving these vector spaces, in giving all of these maps. Of course, they have to be.
It's usually commutative because it doesn't matter how you label.
Yes, this is meant to be commutative, or possibly, if we might say graded commutative, if we're considering a theory with fermions. So this just depends on this set, but of course everything's meant to vary smoothly when we move the points around. The trouble is, what properties do you want of these functions? It's rather difficult to axiomatize them in that form. And the motivation for the way you try to say what properties they ought to have is that there's a sort of mythology overlying this situation, that you have in your mind that there is some space phi x, so this is a purely mythological space of so-called classical fields, locally defined on x. So they could be any kinds of things like functions with values in some vector space, or even a curved manifold, or connections up to isomorphism or whatever. And there's meant to be some, so they're meant to be locally defined, so they can be restricted at least to subsets x. There's meant to be some action functional, a map on this, which controls the whole situation, in that this is meant to enable one to define a measure, the mu on phi of x, which formally is meant to be somehow written like this. Well, I'm writing it trivially. Somehow like that, whatever that means. It's meant to be something which is weighted very strongly by this function, so that it's concentrated very tightly on the, because this Planck's constant, which is meant to be very small, around the critical points of S. And of course we've met this structure already in Kevin Costello's lecture, where for him a classical field theory precisely is not all of phi, but just the germ of the infinitesimal structure of this space of fields around the critical set of the function S. So you don't just keep track of the critical set, the infinitesimal labels. That's a kind of classical picture of what we're trying to make here. The relation, however, of this to this picture is that if we really had this measure, then what we would do is define, we would, given this mythological picture, we would define OX as contained in the C infinity functions on phi of x. This would consist of those functions psi, such that psi of a field depends only on the jet called phi x. So its value and its derivatives up to however many orders one likes. So this is a function you can observe just by looking at the field nearby, and this number here is then meant to be the integral over phi x of psi 1, phi k, phi d phi with respect to this non-topological measure. Well, so that's the traditional situation which one somehow can try to axiomatize or try to derive properties from.
Question? Why does the first thing land in C but the action land in R?
Yeah, because, well, these are in principle complex valued functions, for one thing, but also they're much better answers that maybe I should have said it was a complex valued measure, but I'm really cheating by saying I'm moving from Lorentz spaces Lorentzian metrics to, yeah, it's probably not very fruitful to discuss that because it would take a long discussion. Well, you see, if we were doing this in proper quantum field theory, there would be an I, and there is.
Is that a 1 or an I?
Yeah, I wrote in a 1 because that's what you do in physics. And then I changed it. I wrote an I, then I changed it to a 1 because I remembered that I was talking in a. Yeah. Let's stop showing this. So, about 25 years ago, rather as a joke, I proposed a different way of trying to come at this thing. And since then, the idea has sort of been taken up by lots of people and taken in all kinds of directions that certainly have nothing to do with me. And let me just say it very quickly because I have to begin somewhere and explain, because I think the direction in which I had in mind to take it is not one which has been pursued very much, and I still think there's things to be done in that direction, and I'd like to explain a certain angle on it. So my idea was one which now in this meeting I hardly need to mention, more than mention. I suggested that one could define a field theory in dimension D as a functor from the cobordism category in dimension D to vector spaces. So it's something which, to a closed-oriented Riemannian manifold of Y, with dimension D minus 1, associated with topological vector space, and for cobordism from Y0 to Y1, I'll write cobordism is usually like this, a d-dimensional cobordism like that, with associated a trace class operator.
How did you get this idea?
Well, I remember I drew it there was a meeting organized by Katia and Hepsburg at the castle called Ringberg near Munich, and Witten was giving lectures on what he said on how he looked at this picture and the factorization properties of the integral and how the essential properties that these things have to have with what happened when you divided x into two regions and how you do the integral in this region and that region and so on. And so it wasn't a very big step then if you're a mathematician to sort of come up with this. I said, well, what we're saying is really we have a functor on the cobordism category, and everyone laughed, and that was more or less the end of it for a while. And then we were all talking to each other, and I kept sort of saying, well, it's not such a stupid idea. And then the big step was that I read something about conformal field theory, and then Mike Lapier wrote it down following Witten, really, in the topological case. And then that attracted a lot of attention, and people have talked about it ever since. But so this is the data, and the axioms that this is meant to satisfy are just two, or possibly three. One is that the output should depend smoothly on the data, that if you have smooth families of things on this side, the data on this. I should have written wrote that down. This is actually a trace class linear operator. So there should be smoothness, which I won't say any more about. Secondly, there should be a functoriality property. I'll just write it down as concatenation. That if you string together consecutive subordisms, the operators compose. And thirdly, a tensoring property, which means that if you take a disjoint union of two y's, then this tensors in some sense, and that in particular implies, of course, that for the empty manifold you just get the complex numbers. And similarly, if you put two cobordisms side by side, you get a tensor. So this is a tensoring axiom. And of course, I didn't know about things like tensor categories then, but now there's all sorts of language used to describe these things. So this says that the things are functor in the cobordism category, and this says that the tensor is functor. Well, there are lots of refinements you need to put in very quickly. The only refinement that's actually important to mention in this talk right at the beginning is that already for the definition to make sense, you need to say that h of y is really defined not for y, but for a germ of a D-manifold along y. In other words, you should think of a cobordism as ending. So here's a cobordism x that ends with a y, and you should think of y as really being a little collared thing, the way I do it, bi-collared thing around y, from which another cobordism might then set off. Of course, you need to keep track of the germ if you want to be able to compose cobordisms, because otherwise, when we put two cobordisms together, there wouldn't be a smooth structure on the interface. And a germ means just that this is some D-manifold that contains y in a given way, but you identify any two of these if they agree in a common neighborhood of y. That's at least a very simple definition. And how does it give back this kind of data? Well, the idea is, you see, if we go back to this picture, imagine X is a closed manifold, just for simplicity. Imagine you cut out a little tiny piece around each of those points, and that gives you something which I'll call X hat, which is, so this is X minus little disks. Around those points. This is a cobordism from the disjoint union of the boundary of the disks to the empty manifold. So according to that principle, that gives you a map from the tensor product of the boundary of these disks. Gives you a map to H, the empty manifold, which is the complex numbers. So if we take this to be O of xi, then we're in good shape. Well, of course, that doesn't quite make sense, because what size of neighborhood do we take? Well, if we want to, so the natural thing to do is to define O of xi, not just for one particular neighborhood, but as the inverse limit over all d, such that xi is in the interior of dxi space associated with the boundary.
How do you get that?
Well, you see, if this is an ordered system by one being included in the interior of another. We have a point x in the middle. We look at the nested family of little disks. We order them by saying one disk is in the interior of the other disk. And then you think of the cobordism formed by the difference between the two. Think of it as a cobordism going outwards. So it will map the space for this sphere to the space for that sphere. We take even the system. So that's why it gives us this kind of data. Now, the kind of question that I was interested in at the time that made me suggest this was the question of when two field theories are the same. At the time I just started working on things like loop groups and so on, and I was aware of these theorems, like the boson-fermion correspondence in 2 dimensions, the equivalence between what's called the Sine-Gordon theory in 2 dimensions and the Turing model. So there are theories defined in completely different ways which were said to be equivalent. And the art of showing they were equivalent was definitely an art rather than a science. Because, you see, when you describe a theory in this way, it's a little bit disingenuous. Because what you actually do in practice is some particular elements in this vector space, some actual fields which are defined from the nature of this mythological geometry. And you adjoin new elements to those spaces by constructing things in cunning ways using normal ordering and this and that recipe beloved of quantum field theory to produce new elements in here which you say are local fields. And you never quite know when there might be some really good trick which came up with a new local field. So these things are very, very open-ended. And of course they're infinite dimensional. And so the theory was a very murky piece of data, and it was therefore extremely difficult to think of what it might mean to speak of the, say, the moduli space of 2-dimensional field theories of a certain type, or something like that. And why might one want to do that? Well, I said above 2 dimensions, of course people think those field theories are very rare indeed. But in 2 dimensions, for example, there is a beautiful class of so-called conformal field theories, and I've then begun to hear about string theory, and string theory more or less begins from the observation that a certain class of 2-dimensional field theories, in this definition, which are conformal, that is to say, they depend on they're defined on the cobordism category of manifolds equipped with a conformal structure rather than a full Riemannian structure. Those theories are certainly not very numerous. They fall into finite dimensional families. Those families are meant to be some kind of generalizations of solutions of Einstein's equation by the map which to a manifold assigns the 2-dimensional theory called the sigma model, in which this is the space of maps from a varying 2-dimensional manifold X into a target gravitating manifold, spatial manifold. And the action S is just essentially the usual action you use in the theory of harmonic maps, the energy of the map is critical points of the harmonic maps. Well, there's a lot more to be said about that, but there's a kind of map, one hopes, again, to this day only not really defined, which to target Riemannian manifolds which are theories, and solutions, Ricci flat manifolds, are meant to correspond to conformal theories. Well, if you're more ambitious still, there's meant to be an even bigger picture that if you take a general Riemannian manifold as target, then of course we have the space of all manifolds and we have the Ricci flow on that. On the other hand, on theories of this kind, or this kind really, there's an obvious one-parameter group acting which simply composes with the functor from the cobordism category to the cobordism category, which just multiplies all the distances by something, just rescales the metric. So there's an obvious one-dimensional rescaling there, and if you are very, very optimistic, you can hope that 2-dimensional theories are somehow generalized manifolds, and the scaling flow corresponds to the Ricci flow. Well, I was at the time very fascinated by the famous paper of Zamolodchikov, which tries to spell that out at least in perturbation theory, in the neighborhood of a conformal theory. And again, that's still a theorem which exists at what mathematicians refer to as a physical level of rigor, I think.
What is the statement?
So I'll make the statement in a little while then. But what Zamolodchikov did was he managed to, starting with a conformal field theory, he managed to parameterize, I'm going to talk a bit more about that presently, the infinitesimal neighborhood of the conformal theory in the space of theories not necessarily conformal. So on this space, you define this germ of the space, this infinitesimal space, the kind of thing Kevin was talking about. He defined a Riemannian structure and a function, and he argued that the renormalization group trajectories were the gradient trajectories of that flow with respect to the Riemannian structure he defined. Before leaving just this general picture, I'll say one more thing. What's the structure of these things? See, I said these weren't algebra, so it has vector spaces. But one thing, at least you see directly from this definition, is that you do have a kind of algebra structure on these things, but an algebra of the up to homotopy type that we've been hearing a lot about. So suppose you're near a particular point x in x. And suppose you take a particular small disk around a D. Then, of course, this will normally inject into the space associated to the boundary of D. It will be some kind of dense subspace. You should think of these inverse systems as strongly contracting operators, so that you can think of this as some kind of completion of X. The course of the completion, the further out you go in the disk, the bigger the disk is. Well, supposing you pick a particular little disk, well then you can, of course, consider your sets of k points in the interior and take out little tiny disks around them. And you'll see what you immediately read off is that you always have maps, whenever you pick k points in the disk, you will always have maps to this, but I'm calling that the completion of O of x. So that if you're prepared to complete the space of observables at a point x, then the observables at nearby points can be multiplied, and the multiplication will presumably vary smoothly when you move the set of k distinct points round about in the neighborhood. So this is trying very hard to be a commutative and associative algebra, but we have not one product, but we have a product, a family of products parameterized by this configuration space, and the maps vary continuously. So that is, in the most literal sense, an algebra with a product defined operatically up to homotopy. And of course, I haven't introduced any cochain complexes or things here, but of course we might go on further and be led to do that. But for the moment, I'm literally talking about composition laws defined up to homotopy in the obvious topological sense. So we have this very nice structure of things which are close to being algebras and not quite algebras. Well, so why, suppose one had this picture, suppose one is interested in trying to make a moduli space of theories, then obviously the first thing you need to know is what are the infinitesimal deformations of a theory? What's the tangent space for the space of theories at the theory you have? Now, you see, from the point of view of the physicist's mythology, it's meant to be kind of obvious what the space of deformations is. because the space of deformations is meant to be the space of point fields. So I'm going to say more about this presently.
Space of what?
The space of fields of X. I'll say it very roughly, and then I'm going to try and hone in on making it a bit more precise. You see, supposing we have a theory that we're going to deform, and it gives us this map. And now we're going to deform the whole thing. Now the idea is that the definition allows us to chop this cobordism up into pieces. Those pieces can't be too small because they're all sort of slices. But supposing we could chop it up into little bits which just moved us on by a tiny little piece of X step at a time. So that this map, U of X, was a composite of a whole lot of pieces made up of contributions coming from little tiny steps in the cobordism which were actually small. Well, in that case, you see, because this U of X is meant to be the product, the composite of all these things, if you make a small change in it, then the first order change will be given by making a first order change in each one of those things. And the change is meant to be completely described by what the change made in an operator associated with a typical tiny little piece of X. And that's something which you ought to be able to see entirely in the space associated to that little boundary. And that ought to be a field defined at this point. In other words, the general philosophy is that when you have a deformation, there should always be some field in OX. And of course, so I'm going to come back to this point, but let's suppose for the moment that we can identify all of these OXs with each other. Assume that the manifold looks the same in the infinitesimal neighborhood of every point. I'm about to come back to that. Then supposing you pick something there, then you'd like to say that the only deformation of the theory are ones of this kind, where the deformation of the U of X is somehow got by integrating something which I'll call Ux psi, x, dx over x, where U of X psi x is the following thing in terms of my picture. Let's think of X now as a cobordism. Here we have an X there. Make a little hole around it. Then we get a cobordism from X minus from Y naught disjoint union boundary of D to Y1, and tensor map from H Y naught tensor, I might as well say O of X into H of Y1. And if I insert psi in there, I go from H of Y naught to this by tensoring with psi, and then do this operator. That's the thing which I'm calling that. So the idea is that infinitesimal deformations are all created by fields. And that goes back to the mythological superstructure, where you see the theory is meant to be completely defined by S. And if you make a small perturbation of S, S is meant to be local, so it's meant to be an integral over the manifold X. If you make a perturbation in this, you can take the small change in S down into the integrand and put it into the thing that you're integrating there, and you'll see that you have inserted the field. Well, to make any sense out of this, you certainly need to have some more structure which tells you. So I would like to prove some theorem like this. Can I actually prove a theorem of the kind that the perturbation of this theory is somehow given by a field of a certain kind? I hasten to say that I can't prove such a theorem, in case any of you get too hopeful. But we need to know something more about this system OX, which is the inverse limit. Like this. Well, the case that I started off by studying, you see, was one which one understood rather well. Because if we are in the case of two-dimensional conformal field theories, then whenever you have, then any two disks are the same. We have a surface, we put a disk in it, then any other disk is a conformally identical disk just embedded in it. So all of these spaces are the same. Let's just call them H. And certainly the semigroup of embeddings, or conformal embeddings of the disk in the interior of the disk, this acts on H by trace class operators. You see, because all the disks are the same, all they're doing is putting one inside the other and looking at the associated coordinates. Well, in fact, the action that I'm interested in is the embeddings which take 0 to 0. So I'll put a 0 there to indicate that the map preserves the center of the disk. So here is some infinite dimensional semigroup which actually acts on this. Then you can say that these fields are not all just the same. There are different kinds of fields. For example, this, you can, by differentiating at the identity, this maps into C multiplicative. If they're conformal maps, we can think of D as the complex disk. So a conformal map from the disk has a derivative which is a non-zero complex number. The semigroup maps to that. No, it's a semigroup. They're just embedding the disk in the disk. There's just one disk.
All the disks are
Yeah, so D, we can now think of D as being the standard two-dimensional disk, which we're contemplating putting in the manifold in a certain way. Well, you see, so we might look for vectors in this space. So this system, we can pick a cofinal system, in fact. Around any point, we can pick a cofinal system like this, where we're just embedding the disks in themselves concentrically, making them smaller and smaller. So we actually have a kind of rather obvious action just of the semigroup of linear centered embeddings of the disk, conformal disk in itself, by contraction. Well, in particular, then you might look for eigenvalues of this action with respect to this homomorphism. You might look for a psi in here, such that when you contracted it by, suppose we take the diffeomorphism theta, such that theta dash at the origin is lambda, you might look for a psi such that when you apply theta to it, you just got lambda to the k psi. Now, this action doesn't need to be holomorphic, so in fact we could also contemplate things such that this was lambda to the p, lambda bar to the q. So we could look for things that behave like that. Supposing we had something that behaved like this, then what could we do? The resulting field, well, we can identify all of these things, but in order to actually put the field for the standard disk into a point on the manifold, we of course have to choose a coordinate patch, and putting it in by a choice of coordinate patch if psi behaves like this will tell us that the way psi behaves in O of x when we choose our coordinate patch is simply like a differential form on the manifold. We should really think of psi as being something like dz to the p dz bar to the q. So we will say these fields have properties which enable us to think of them as differential forms of various degrees on the manifold, or at least some of them do. I mean, we could have something which behaved as wasn't an eigenvalue of perfection, but which depended on higher derivatives and so on. That would be some kind of derived field. The ones that have this property in the traditional language are called primary fields. Now, what you immediately see is that if you wanted to form the theory, what you want to look for is a field which is going to behave like a volume element. So in the formal picture, you would say that the deformations of the theory are given by fields which, for which when we, you see I tried to make, in order for that really to make sense, I want this psi of x to behave like a volume-like thing on the surface. So just a particular class of fields would be the infinitesimal deformation. But you see, that's for two-dimensional conformal theory, and what happens more generally? Now, I think I don't know anything better than to try to introduce an axiom.
Last thing you said, you would make P and Q be 1 and 1?
That make P and Q be 1 and 1. Yeah. So, now I don't know how to go any further without introducing some kind of axiom. You see, this inverse system could be appalling for all we know. And this is closely related to what's called, I think, asymptotic freedom in quantum field theory. I mean, if we have a nicely behaved theory, then when we look at it at very small distances, then it will become, if we're lucky, something comparatively simple, where a thing behaves just as it would just as some simple theory in Euclidean space would. I mean, when we look at a manifold with very high magnification in the neighborhood of the point, we get a little bit of a Euclidean vector space locally in the limit. And we can ask for theories which behave nicely with respect to expansion and contraction there in the way that conformal field theories do. And I don't see any way of really going anywhere with this kind of structure unless one's prepared to add an axiom that this system behaves, that this inverse limit in the general case is asymptotic to something conformally invariant on Euclidean space. So that actually this space O of x is naturally attached to the metric tangent space at the point, that the tangent space with its Riemannian metric, and hence the conformal group locally acts on it, and we can classify its elements according to the kind of field they are, and so on. Now, that certainly doesn't have to be true, but in all the theories that one can think about, I mean, I'm not going to have time to talk about it in this talk, that's true. I mean, there aren't very many theories where one can say anything mathematically precise, but they certainly all have that property. And notice that this is very like what happens in scattering theory, where you have some unknown system and you are saying that as time tends to infinity, you're assuming that it's somehow tending to be a very simply controlled free theory. We're doing that with respect to the closing in on the point. But even so, this axiomatization is not going to get us very far unless we have some more properties. Because, you see, if we wanted to start proving something of the kind I was saying, we want to be able to cut the manifold up into pieces which are actually small. And the trouble with my axioms, as I gave them, is that they're not restrictive enough in that they don't tell you in what sense, if any, the space associated to they don't tell you in what way, if any, the space associated with y depends locally on y. And so what would that mean? See, y is a closed manifold. Suppose we cut y into two parts, y1 and y2, by some submanifold z, which would be of codimension 2. It would be very nice if, for instance, one could say that h of y were, for example, a tensor product like this. If you could associate a vector space to a d minus 1 manifold with boundary in such a way that this was true. Now, if that were true, however, physics would be extremely trivial, you can easily see, because no influence would ever travel from one region to the other. And so the next best hope is that one might be able to say that these, so let me try and say just a little bit more about what obstructs this from being true. The simplest case to study is a free field theory where the imaginary space of fields consists of real valued functions and the action is the harmonic action, maybe with a mass. So this would be called free scalar field theory. In that case, we have a classically well understood candidate for this, in which h of y is the L2 functions, in a certain sense, on the space of fields on y. So we take our Rackham as omega naught. Again, we don't have time to say anything in detail anyway. We consider the space of C infinity functions with real values on y. That would be the field restricted to y. And that's a vector space, and we would take the L2 functions on that. Now, you can make an L2 space, a Hilbert space, out of functions on the vector space whenever you give a positive definite quadratic form on y. Sorry, on the vector space. So in order to define such a space, we need to give this vector space and a Gaussian function defined by a quadratic form, which enables us to define a Gaussian measure. That will be the free bosonic field theory. I just want to say one short thing about that structure. What is the quadratic form that we have to use? So we want a quadratic form on well, you compare this space with the top forms and think of it like this. Think of a quadratic form as a map like that. And one way of getting such a map, and that turns out to be the right way, is to say that when we're given y, we contemplate making it the boundary of a manifold x with dimension 1 higher. Now, you mightn't be able to do that, but just suppose for the moment you can. And then this equation corresponds, of course, to the Klein-Gordon field equation. That has the property that if you give a function on the boundary, a phi there, there's a unique way to solve the Dirichlet problem and get a solution of the equations, critical point of S, extending it inwards. And then we can look at its normal derivative. In other words, we can take phi, defined on y, we can extend it to a solution of the Dirichlet problem. So this is to give an x And then we can take D of that and take star. That will be a top, and then we can restrict that to y, and that will be in omega d minus 1 of y. Okay. So phi goes to star d hat phi restricted to y. That's a positive operator, trivially, just by integration by parts. And it's what we want. This defines space. And the remarkable thing about this is that the operator, this extending and restricting to the normal derivative, it barely depends on x. It does depend on x, of course, but the operator that we get, the quadratic form, depends only up to what are called smoothing operators, so very small operators, on the infinitesimal geometry in the neighborhood of y. So we get a well-defined space, this. On the other hand, this operator is a pseudo-differential operator. So if you were to try to cut y into two parts and look at the quadratic form, there's always a cross term between functions defined here and functions defined there. Although you can choose x in different ways and choose different representatives of the quadratic form, you can never make a sharp cutoff which would enable you to factorize the Hilbert space. So, let me make this one quick reference again to Kevin Costello's talk. If we're working in the context of deformation quantization, this becomes a bit easier in the sense that we can, the spillover will then only involve the infinitesimal neighborhood of the cutoff. That's to do with the fact that if you do an integral, supposing you do an integral like this, f of t e to the minus t over h dt, where f is a function with compact support on the line, then you know that asymptotic, this has an asymptotic expansion in h of the form h to the k and the k plus h to the k plus 1 times the k through the origin. So this thing, asymptotically in h, only depends on the infinitesimal behavior of f in the neighborhood of the origin. And similarly with these pseudo-differential operators, the spillover can be reduced to something actually on the interface if you work in an asymptotic expansion in terms of some small parameter. And that would take one back to the picture which Kevin was telling us about.
Can I ask you a question, Graeme?
Sorry?
Can I ask you one question about this picture? So, it's like you're saying that the Cauchy data is always a symplectic manifold.
Yeah.
And would you have this Hamiltonian flow, and you're going to get a corresponding time derivative. So you're going to get a corresponding Hamiltonian function on the symplectic manifold Cauchy data. That's basically what this.
Sorry, I was trying to say things maybe too quickly. The symplectic manifold will be the direct sum of these two spaces,
yes.
And I was quantizing it.
And but the quadratic formula in that looks like the Hamiltonian for the time derivative.
It's the Hamiltonian for the time, in imaginary time going inwards, indeed, yes. Right, that's right. You see, I was taking, as it were, a genuine quantization rather than a deformation quantization. And this schematic argument is meant to explain that if instead of taking an actual quantum space here, I'd done a deformation quantization of the space of fields, I would have got something that was local in a stronger sense. But I'm almost out of time, so I better just say some things very quickly. I meant to stop at 42. So let me just try and say some things very quickly. So I was very interested in what you can do in this picture in the way of factorizing the space. can one, for example, associate an algebra, perhaps a von Neumann algebra or something, to a cut in Y, so that these things existed as modules over that algebra, and you've got, you see, could you, for example, define an algebra associated to Y and have a formula of that kind? And what I was able to prove in a variety of cases was that you can do that, and a rather intriguing thing happens, which I wondered at first if it was just to do with the nature of my examples. So I'll just try and say that very quickly and stop. So I was able to prove that a patching together theorem like this in the case of free field theories, where in some sense everything is meant to be very well understood already, and also two-dimensional conformal field theories. And I wonder if that was for the following reason. That in the cases where I could do it, the thing about the spaces H of Y was that they could be characterized as representations of certain groups simply depending on Y. In the case of this example, for instance, H of Y carries a representation certainly of the C infinity functions on Y simply by translating. It's L2 functions on a vector space, so we can translate. And we can multiply by elements of the exponential of the dual, so exponentiating things in that. So this is a representation of a certain infinite dimensional Heisenberg group made from this space and its dual. And this is characterized as a representation of that of a certain class. Similarly, in the conformal field theory things, the spaces are characterized as representations of loop groups and that sort of things in 2 dimensions. Now, it's sort of well known in quantum field theory that you can't do anything like that in more seriously interacting theories. The way it's expressed in the traditional language is the field, I'm using fields which are not smeared in time. These are the operators I will be acting with are things defined on the time slice Y and don't need to be averaged out in time. But so I eventually came to the conclusion that one could replace these Heisenberg groups by something more in the nature of A infinity algebras, because when we had something like well, I now better reverse this a little bit. So we have our Y, which we're trying to cut into Y1 and Y2. And what I found was that if you enlarge each of these things a little bit, so we have a Y1 plus and a Y2 plus, we can assign a space to each of those and keep track of the fact that it's a representation of a group associated, this one is a group associated with that interval, and this one is a representation of a group associated with that interval. And by making an algebra which is a mixture of these two groups, one could make a tensor operation of this kind. So what the actual object was, which we associated to Z, was when we have something Z in codimension 2, we consider all sorts of little flaps of codimension 1 manifolds with boundary Z, which stop after a certain, they only go a certain very small distance. We have a group associated to each of those things, and what you have to associate to the HY1 associated to a Y1 with boundary Z is actually a collection of spaces, one for each little flap like that, with a family of maps relating them, which in operator algebra theory is essentially the Tomita-Takasaki flow associated to any one of them regarded as generating a non-topological. Well, so I was able to do such a thing, but then I believe, and I haven't really worked out this very thoroughly, that one can replace these groups by simply the vector spaces freely generated by all the collections of the field operators, those OXs I had at the beginning, the configurations of points in those little sectors. And so one should really have a collection of vector spaces associated to each of these little flaps with maps between them parameterized by the configurations of points in the little sectors. So it's really trying for me to stop, so I really must stop. And I have to say that even when you do that, that enables you to, I wanted to say a little bit more and explain how, if you had, say, a surface triangulated very small, that would enable you to express the partition function for the surface, the map associated with the whole surface, as a composite of contributions, each coming from the boundary of a little tiny region in the surface, which would be a boundary which had angles. But even then, for reasons I can't explain now, that still is some distance short of being able to prove a genuine perturbation theory. I mean, that's the genuine theorem that says that perturbation comes from a field. You still need some more regularity, which I haven't managed to formulate. So I'll stop there.
Questions or comments?
Could you explain a bit more why this data get flow appears?
Not really. I mean, that would be a long story, I'm afraid. If you're around this afternoon or something, I'm happy to try. I mean,
I was just wondering, so would you say that it's an underlying philosophy that you're kind of starting from an actual theory, you're trying to deduce what a structure is by using physical equation and the infinities or the sharpness, the infinities that are created by a sharp cut and so on are modified if you spread things out. But when you modify in this way, you will create these infinity structures.
yes, that's good. I was trying to, perhaps I can make one way of cheating, but I was going to say, this notion of a field theory is a little bit like, I feel, even Madsen pointed out, that you could suddenly find out all sorts of things about the space of manifolds once you recognize that the structure has this very rigid property. So it's very important somehow to see what the property of being an infinite loop space was in this case. And I'd like to see that it's something like this here. At the same time, I'm also somewhat reacting in the opposite direction from the modern tendency to want to cut down and down to lower codimensions and say you build everything up from a D category associated to an infinitesimal neighborhood point. I wanted, I'm trying to say that all of this structure is actually implicit in the top two levels, because already there you see this composition law associated to d-tuples of points in little neighborhoods, and that is somehow where everything is really visible.